So we have an acceleration problem. And remember that acceleration is a vector quantity. That means it's got both direction and magnitude. And so in this case, it's a delivery truck. Very exciting. It's actually delivering dynamite. And initially, it is traveling 50 kilometers per hour west, 60 degrees to the north. 15 minutes later, which is a change in time of 0.25 hours, it is traveling east 60 degrees north. And so not only has the magnitude of the velocity changed in this case, the direction of the velocity has changed as well. And so we have to consider both of those when we're calculating acceleration. Now, you can tackle this problem a few ways. You could take these two vectors and you could find out what negative v1 is. In other words, turn it around, place them tip to tail, and make a triangle. And then solve the triangle using either the cosine law or the sine law, whatever's appropriate for the information that you've got. I much prefer to use a components approach. And so basically breaking it up into perpendicular components. In this case, we are going to break it up into the easterly component and the northerly component, at least treating east as positive, just like as if it was the positive x-axis, and treating north like it was positive, just like as if it was the positive y-axis. Now, one thing that I've always found is a little bit useful is to make a little table like this so that we can keep track of each component separately. We can calculate the change in velocity of the two components, and then we can reconstruct our vector when we're all done and find out what the acceleration was. Okay, so let's do it. 50 kilometers west, 60 degrees north. I'm going to find this vector, which is actually going to be an easterly vector. For now, let's break it down. This one is actually negative 25 kilometers per hour, and that is east. Now, really, it's 25 kilometers to the west, but if I'm standardizing on east, I'm going to call it negative 25 kilometers per hour to the east. I'm now going to get the component of this vector, and I'm just using SOHCAHTOA each time. And so 50 kilometers per hour, and this is going to be the times the sine of 60 degrees. And so this winds up being 43, and I'm going to keep a decimal place, 0.3 kilometers per hour, and this one is to the north, and it's positive. Okay, so I'm just using SOHCAHTOA, the nice, easy sine and cosine and tangent of a right-angled triangle. Okay, now we need to break V2, 80 kilometers per hour, east, 60 degrees to the north, into its two components. And so if I do 80 kilometers per hour times the cosine of 60 degrees, I wind up with 40 kilometers per hour. And this is going to be positive and to the east. If I go for my northerly component of this velocity, I find out that it is, I'm going to carry some extra decimal places throughout my calculation in this case, kilometers per hour, and that is to the north. Okay, we've got both of our components. Always draw this out. It helps me to know that you know what you're doing. It also helps you keep the information organized, even though this might look an awful lot like a dog's breakfast at this point. Okay, let's break V1 into its two components, or at least let's record them in here. So the velocity to the east, and this is going to be in kilometers per hour, so that I don't have to write the messiness down. It's negative 25 kilometers per hour to the east. That's my initial velocity. so that's 25.98, and that's kilometers per hour to the north. Okay, so this is my delta V for the easterly component. This is my delta V for the northerly component. And now what I'm going to do is I'm going to reconstruct them. So V2 minus V1. And that is V2 minus V1. So that's 65. And this is 26. Now that I've calculated the size of the change in velocity of these two components, I can add them together to get the total change in velocity. And so the final change in velocity, and this is overall, I can just calculate using the Pythagorean theorem. And so this is going to be the square root of 65.0 squared plus the square root of 26.0 squared, and that is 70 kilometers per hour. Because it's acceleration, it has both magnitude and direction, so that's not 70 kilometers per liter, by the way. And so I have to figure out the angle of the change in velocity, and so I can just use the inverse tangent to calculate the actual angle. And so the inverse tangent of 26 over 65 is 21.8 degrees. And so overall, my change in velocity is 70 kilometers per hour, and this is east, 21.8 degrees to the north. That's my change in velocity, and I know that my acceleration is change in velocity over change in time, and so this is 70 kilometers per hour east, 21.8 degrees north, divided by 0.25 hours. And so 4 times 70 is 240. So it's 240 kilometers per hour squared east, 21.8 degrees north. And if I go back and check, the original problem actually specified there were 3 significant digits in each of these. And so I have to make my calculations accurate to 3 significant digits. Okay, so that is calculating acceleration from 2 velocities given both a change in magnitude and a change in direction. And I do recommend this table. It does serve to organize your answer and keep those components nicely separated. When you're done, put it all back with the diagram and insert it into your calculation.